It's okay? Yeah, is it okay now? Thank you. So also thank you for this your kind introduction. This is okay. So it's my pleasure to present you a lecture on anaerobic digestion of various residues. And this is the program of the presentation. I will first make an introduction to anaerobic digestion. Then we will speak of various feedstocks that can be used for this process. I will show you the anaerobic digestion mechanism. We will then speak about the biogas composition and treatment. Then how we can carry out anaerobic digestion at laboratory scale. And then further we scale up to full-scale technology. And finally, I will show you some picture. Well, what is anaerobic digestion? It is a natural process that was discovered in 1876 by Volta because of the marsh gas he discovered that can burn. So it is a biological process which is made by a consortium of various microorganisms in absence of oxygen. And this microorganism converts organic material into biogas, which is composed of methane and CO2. And you can use the methane as renewable energy by cogeneration to produce heat and electricity. You can also produce a biofuel and inject it into the natural gas grid when the country has such a grid. And also the undegraded material, which is composed of a not biodegradable fraction of the substrate and is enriched in the nitrogen and phosphorus, as nitrogen and phosphorus are not degraded, and it may be used as fertilizer. Concerning the organic different feedstocks, it can be any kind of organic matter, sludge, manure, agricultural residues, energy crops, also municipal solid waste and industrial wastewaters. So the various application will be first and now more and more the production of renewable energy. You can also use anaerobic digestion to remove carbon of the wastewater. You can reduce the sludge to be disposed of, the sludge from wastewater treatment plant. You can also make the treatment of solid waste, either agricultural, industrial, or urban. You can use anaerobic digestion for soils decontamination, with organochlorine as an example of chemical contamination, and also to treat the wastewater with colon. Well, 1 cubic meter of methane is equivalent to 8,570 kilocalories, which is equivalent to 1.15 liter of gasoline, 1.3 kilogram of charcoals, 9.7 kilowatt hour of electricity, and about 1 cubic meter of natural gas. And when you use anaerobic or aerobic digestion to treat wastewater, I have put it here a balance of COD, chemical oxygen demand, which is a measure of the pollution in a residue. So for 100 kilogram of COD, in aerobic process where you provide some oxygen, you need 100 kilowatt hour of energy for aeration, and at the end you will also yes, sorry. Yes, at the outlet of the aerobic process, you will still have only 2 to 10 kilograms of COD, but you will have a high production of sludge of about 30 to 60 kilograms. And also, you will have some losses of energy. The same 100 kilograms of COD, which are treated by anaerobic process, we produce only 5 kilograms of sludge, and as a positive outlet, you will have 245 kilowatt hours of energy. This is the main advantage of this process, but as a disadvantage, you still have higher concentration of COD in the effluent, from 10 to 20 kilograms COD. So most of the time, you should add an aerobic process to finish to remove pollution. If we look at the carbon mass balance, so for 100 kilograms of carbon, after our anaerobic treatment, you will have 55% of methane, 10% of sludge, 10% of pollution, and also 25% of COD for the anaerobic treatment. For the aerobic treatment, you will have 50% of COD, 45% of sludge, and only 5% of pollution. Now, as a more general balance for anaerobic digestion, the waste are composed through of carbon, but also hydrogen, oxygen, nitrogen, and phosphorus. So it is mainly the carbon which is concerned by the degradation during anaerobic digestion to produce biogas and methane and CO2. And in the digestate, you will have some stabilized carbon, hydrogen, oxygen, all the nitrogen, and all the phosphorus. That's why it will be enriched in the microelement, nitrogen and phosphorus, and also in stabilized carbon. So it can be used as organic fertilizer. In the case of phosphorus, you know, there's a concern of the disponibility of phosphorus. 100% of this phosphorus is recovered in the digestate, and around 70% in the solid phase of digestate after phase separation. So now I look more precisely on the fate of nitrogen. In your substrate, you have either organic nitrogen and mineral nitrogen ammonium. After anaerobic digestion, you will convert one part of the organic nitrogen into ammonium. And after phase separation, if you have the solid fraction of the digestate, it will get the higher percentage of the organic nitrogen, whereas most of the ammonia will be found in the liquid fraction of the digestate. So, yes, for this first party, let's move to the feedstocks for anaerobic digestion. First, you can have most of the wastewater from industry, mainly food industry, paper industry, and pharmaceutical industry. So you will have some wastewater from drinks, brewery, juice, distillery, from any food, from dairy, from potato processes, from sugar, from vegetable, from fermentation, from starch, and also few wastewater from chemical industry and effluents. Among the solid residues, you can treat the sewage sludge from wastewater treatment, the wet and dry animal manure or dung, the organic fraction of municipal solid waste, the waste from plant and animals from food processing and slaughterhouse, food waste from restaurants, as well kitchen and garden waste, waste and byproduct from forestry, and also some residue from crops. And in some countries, you can grow also energy crops. In the next slides, I will show you the potential of various substrate. It is usually expressed in cubic meter of methane per ton of waste. In this case, it is the ton of wet waste, and it is usually related to the total solids of the concentration of this waste, because the water content will not give any biogas. So for the sewage sludge, you can get 40 to 75 cubic meter of methane per ton of waste. From the manure, from 14 to 18, higher biogas recovery from the poultry litter. Food waste, which are energetical, and the fat is very calorific, so it gives high energy production. So from food waste, you can recover from 60 to 110 cubic meter per ton of waste. Animal byproducts are also interesting, with up to 150 cubic meter. And also after you have organic municipal solid waste, around 100. Energy crops also are interesting, with more than 100 cubic meter. From the sewage sludge, they have to be thickened before anaerobic digestion. I will show you later, we need to heat the digester. So if they have too many water, you need to heat the water, which is a waste of energy. And among the different sewage sludge, the primary sludge have a higher methane potential than the waste activated sludge. And among them, the high rod processes will be more interesting than the extended aeration process. Now, let's see the anaerobic digestion mechanism. It is it's a biological process which is made of 4 successive steps, and each step is carried out by different microorganisms. The first step consists in the hydrolysis of the macromolecules into soluble monomer. It is the hydrolysis step. Then you get an acidogenesis, where you will convert these soluble monomers into organic acid and alcohols. And then the acetogenesis will use this substrate to produce acetate and also CO2 and hydrogen. And then through the methanogenesis, you will produce methane and CO2 on one way from the acetate, and on the second hand from the CO2 and H2. And this is the methanogenesis. So, as a summary, for wastewater, we will have 2 main steps. The first, because they are liquid effluents, so more or less all the components are already soluble. So you started with soluble and directly with acidogenesis, which will produce the VFA, means volatile fatty acids, and CO2. This is a quite fast reaction. And after, you will have methanogenesis, which will convert the VFA into methane and CO2. Let's note that for acidogenesis, the microorganisms are bacteria, different species of bacteria, but methanogenesis is made by archaea. And this reaction is slow. So it will be the limiting step of this process. And if you produce too much VFA, you will decrease the pH, and you can observe an inhibition by the overload of the reactor. For the solid residue, we have another step, which will be the hydrolysis and the conversion of complex COD into monomer. And this step is generally slow. So after you have the same step as before, with two slow steps, hydrolysis and methanogenesis. So according the condition, either hydrolysis or methanogenesis will be the limiting step. To go deeper within the mechanism, so first you will have, your substrate is complex particulate organic matter, but you will have some inactive or deaf microorganism which be used as a substrate. All these substrates can be split into inert particulate and soluble particulate. And after it, you can share it between carbohydrates, proteins, and lipids. They are the main components of the substrates. So the carbohydrate will lead to some monosaccharides, the proteins to amino acids, and the lipids to long-chain fatty acids. Then the acidogenesis from the monosaccharide will lead to the production of acetate and propionate. Also, you can have valerate, butyrate, and hydrogen. After, you will have some conversion of acetate and hydrogen. And also, you have this scheme from LCFA. And finally, you will have the methane production, both from acetate and hydrogen. And, and all these steps are carried out by different microorganisms, which after working will die and be lysed, and each kind of microorganism can be used as a new substrate for the later. And this is, I already have presented you the biological mechanism, but in addition, you have some transfer from the liquid to the gas, because the gas is produced in the liquid, and then you will have the transfer into the gas phase, and also you will have to take into account the growth of microorganisms and their death. This is all. These two slides and the previous one are taken from the anaerobic digestion model at IDMM from Boston. Alors, the microorganisms, they need some regulation in the temperature. They can be either mesophilic like us, and the temperature, the optimum temperature will be between 30 and 37 degrees. But there also are some thermophilic ones. We are working at 50, 55 degrees. The pH, the optimal pH range is for the methanogen, which are the most sensible. It should be around the neutrality from 6.5 to 7.3. You should also have a negative redox potential. That means the absence of oxygen. Ideally, the substrate composition ratio with C, N, NP, carbon, nitrogen, phosphorus should be around 150, 4, and 1. The microorganism will need some oligo elements, iron, nickel, magnesium, calcium, sodium, and cobalt. And also the alkalinity in the digester should be around 1 gram per liter of equivalent carbon calcine. There can be different inhibition of the anaerobic digestion. First, by the VFA. I showed you previously that if you accumulate the VFA, the pH will decreases and it will be inhibit the methanogens. It can be also inhibited by nitrogen, by hydrogen, which is an intermediate reactant. So you should consume it as soon as it is produced, and the partial pressure should be between 10-6 and 10-4 atmosphere. It can be also inhibited by H2S and some some metal concentrations if they are too high. Some organic compounds, such as micropollutants, can also inhibit the anaerobic digestion, but also we can develop some mechanism of adaptation of the microorganism. The hydraulic retention time may be from few hours in the case of wastewater to several days, for example, 20 to 30 days in the case of mesophilic anaerobic digestion, or it can be lower for thermophilic with 10 to 18 days, or some digesters have several months retention times. It is the case of energy crops or manure, which they can have 2 to 4 months retention time. So high retention time means high digester volume and so high investment cost. We also make the differentiation between liquid processes, where the total solids are lower than 20%, and dry process or high solid content process with dry matter up to 20 to 40%. There are some definitions. For the hydraulic retention time in continuous process, you will divide the volume of digester by the flow rate of the feedstock. It can be different to the solid retention time of a sludge edge, where in this case you will take the amount of the sludge in the digested divided by the amount of sludge you will draw every day. So the solid retention time, so the retention time of the microorganism should be high enough to keep the microorganism in the digester, and for mesophilic process, it should be higher than 10 days. The organic loading rate will be calculated by the amount of COD introduced in the reactor every day, divided by the volume of digester. This is in the case of wastewater. And for solid residue, it will be the amount of volatile solids, which is equivalent to organic material introduced per day, divided by the volume of digester. You can also have a massic loading rate, which will be the amount, the mass of CO2 introduced each day, divided by the mass of microorganisms in the digester. So maybe you can see if there are some questions or.
Okay. There is one question from Mulyadi Dil. Wait, can we see the? So I will read the chat, the question. So Mr. Mulyadi asked, can we control the type of anaerobic bacteria that we will grow on the media in the process of decompositions of organic matter into gas, and how?
Okay, so yes, they are sure the Clostridium are acting in the first step of anaerobic digestion, but they are also various other ones. I don't remember their name, but they can be lactic acid bacteria or well, I can look for them. If you want to email me, I will give a more precise answer. But I didn't. Can we control the type of anaerobic bacteria that will grow on the media in the process of decomposition of organic matter into gas, and how? Well, the main advantage of this process is to be able to use natural consortia. And in this consortia, there are many species who can act at the same reaction. So it's the advantage. And if you want to control this bacteria, you go more to some more classical fermentation for food processes. So then you will need to some sterilization of the waste, and according the amount which are introduced into the digester, and also the price, the high price of sterilization towards the quite low price of methane, I think it's not very worth to try to do it. And you are doing research related to increasing biogas using Clostridium bacteria in used drum media. Drum media, what is?
Like an oil drum,
Okay.
like, you know, a cylinder tank.
Yes.
Yeah.
So I understand you are trying to make a kind of bio-augmentation. It may in my lab, some my colleague at the some years ago have tried a lot such topics, but it may work in the lab scale. But after, in how will you do in the full scale to have a huge amount of this bacteria? And also, if you take a bacteria from a laboratory collection, it has very, very low probability to survive in the complex organic microorganism consortia.
Okay. Okay, that's quite crystal clear, the answer, Mr. Mulyadi. If you have any follow-up questions, please continue writing your questions. So we can continue, Dr.
So,
Please continue.
Let's jump to the biogas composition. So the two main compounds will be methane and CO2. But you can also have some hydrogen. We have seen it as an intermediary compound. Some chlorine compounds, siloxane, nitrogen, ammonia, hydrogen sulfur, and water. So if you want to burn your biogas just to make heat, you can you have to remove water and H2S. If you use it in a cogeneration to produce electricity, in addition, you will have to remove the siloxane and the chlorine compounds. For biofuel, if you want to introduce your methane in a the CO2, you need a high concentration in methane. And this will be the same for the injection in the natural gas grid, as we do in France. In addition, we must get rid of oxygen. So, to remove water, you can use some condensation instead with heat exchanger, or absorb water on silica or on glycol. For H2S, it may be water scrubbing, absorption thanks to iron oxide, but you can see the reaction. They have the advantage to be recycled and used again. You can also inject a low amount of oxygen in the biogas to oxidize H2S, and then you have solid sulfur. You can use membrane separation, and also as prevention, you can add some iron dichlorure in the digester to avoid the H2S production. To remove the CO2, it will be due thanks to water scrubbing, pressure swing absorption, or absorption of activated carbon, or stripping. For siloxane, more or less the same process, water scrubbing, scrubbing with some amines, chemical scrubbing, absorption, or heat exchanger for condensation. So I have now a few slides to show on how we process at the laboratory scale to study anaerobic digestion. First, the biomethane potential. It is a very famous test, and in the literature, most of the paper use this kind of assessment because it's quite simple, and also you can make a lot of experiments in parallel. So you will put yourself in the conditions which are favorable to anaerobic digestion in order to estimate the maximal production of methane you can extract from the substrate. From that, you will take an inoculum from anaerobic digester. The substrate to degrade with a classical ratio of around 0.5 gram of CO2 per gram of organic matter of inoculum. You will put in the best condition of pH around 7, and you will add some nitrogen and phosphorus, also microelement. After you add all that, usually we do it in 0.5 liter tanks, bottles. So, and the total volume of the bottle is 400 milliliter. So once the bottle is filled, you bubble by nitrogen in order to remove oxygen, and then you will put your experiment at mesophilic 35 degrees or thermophilic 55 degrees under agitation, and for 15 to 2 months or more, you will wait that the production is finished. To assess the biodegradability of the substrate, we consider by, in theory, 1 gram of COD will produce 350 milliliter of methane. In this case, we do not consider the part of COD that will give some microorganism. So at the maximum, the methane yield can be 350, and to have an idea of the biodegradability or percentage of biodegradability, we will divide the produced volume expressed in milliliter methane per gram of COD of the substrate by this 350. After, we will have to measure the volume of biogas which is produced. You can do it either by water displacement. That means that you bubble your biogas in some water, acid water, to avoid the CO2 absorption, and you measure the displacement volume. You can use a flow meter or a pressure variation sent to the law of perfect gas. You will have to know the biogas composition. For that, usually we use gas chromatography. There also exists a system from bioprocess control and PTS, which is an automatic process. The bottles here are the same as I previously showed you, and they have some mixing at with a stick. They are placed in a temperature. Biogas is bubbled into a solution of soda. In this sense, the CO2 is absorbed in the solution, and that at the outlet, you will only have methane that will be measured thanks to this device, which is composed of the same number of cellules as the bottle, and once the cellule is full of gas, it will open and be registered. And here the curves we can obtain. So the first one, you draw the methane volume in milliliter as a function of time. So this is the bottle containing the sample and the inoculum. And also you should make a bottle control with only inoculum, because they always have some endogenous methane production. So what you will do after, you will subtract the methane produced by the inoculum to the sample. And yeah, after you will have to divide the methane of volume by the amount of sample you put in your test, and you will get the production in milliliter of methane per gram, either of wet sample, of dry sample, or of organic matter. In this case, these are real curves from wastewater sludge. And yeah, you can see that after more or less 20 days, it was the plateau was more or less obtained. And this is here where you can calculate the biodegradability. I told you BMP tests are giving an indication of the maximum of methane you can obtain from your sample. In the real life, you will have probably less methane in continuous reactor. So you can carry it out either in reactors, some batch reactor where you put, like in BMP, you put all the sample at time 0, you close it, and you follow the biogas production. And if the volume is high enough, and if you make some repetition, you can get some information of the kinetics. But the most important tries to do is the continuous reactor to be able to estimate the performance you can have at full scale. So this reactor here is the reactor itself. You will introduce every day some amount of the substrate and withdraw the same amount to keep this some constant volume. In this case, you can have the process performance as the methane production and the total solid and organic solid removals. And also, if there are some risk of inhibition, you will solve them in these reactors. So here the curves, you can get it. On the left hand, it is the organic matter as a function of time, and the blue points are the concentration of the substrate. And you can see that after anaerobic digestion, either it was, no, sorry, I made an error. The substrate, the reactor was fed with the sludge at a concentration ranging from 1 to 12 grams per liter. And in the graph, you can see the outlet of the reactor. In the case of some raw sludge in blue and sludge which were protected by thermal hydrolysis at 150 or 170 degrees in green and pink. And usually, yeah, the hydraulic retention time was of 20 days. And we currently say that we must wait the third retention time to take results, because during the first one, the reactor are not stabilized. So yeah, you can.
Hello. I am sorry for a little inconvenience since we are facing some technical problems here.
Is it okay now? Okay. Thank you. So for the two-stage reactor, you will separate the first step of anaerobic digestion and the methanogenesis. So in this case, you can have some acidic pH in the first stage, which is better for hydrolysis, and neutral pH in the second stage. And also, as the reaction is faster, you will have some shorter hydraulic retention time in the first stage. In the second stage, you can use some, we will see it later, some attached biomass process. And also, in this case, we can increase the organic loading rate. The main advantage of the two-stage is the stability, and also they can be applied to solid waste. And of course, the first stage, the main advantage of the first stage is the lower investment. So you will find more often at the industrial scale. Sorry. For wastewater, so the wet process, you will have different two family of reactor. Thank you. Donc, the first reactor family will be the free bacteria, will be the mixed reactor and the contact. We'll saw them later. And after for fixed bacteria, we will have some granules, fixation on supports or membrane reactor. So the easiest, the most robust, simple reactor for anaerobic digestion, wet anaerobic digestion will be the lagoon, and it's only a tank but which is important, which is close to recover the biogas. And in this case, you can have very high hydraulic retention time. So now, for free bacteria, the most common is the mixed reactor CSTR with a dilution rate which is equal to 1 divided by accelerated time should be lower than the growth rate in order to avoid the withdrawal of the bacteria out of the reactor. And so as for, this is a methanogens, methanosate, is 0.1 minus 1. The minimum hydraulic retention time in such reactor should be 10 days. For sludge digester, can be common to have egg-shaped reactors, so they can be mixed by biogas circulation or by mechanical mixing. The shape is either a cylinder, can be about 10 meters, 8 and up to 40 meters diameter. And the egg shape, as you see in the picture, we say they provide a better mixing in the case of sludge anaerobic digestion. The material of this reactor are usually concrete. This is the contact process. It is the same as the CSTR, but at the outlet you have a settler in order to separate the microorganism and reintroduce a part within the reactor. In this case, you uncook the sludge retention time and the hydraulic retention time. You can have also some reactors with compartments. USB, they are very popular for wastewater treatment. C'est upflow anaerobic sludge blanket. We try to have conditions where the sludge will make some granules, so they can become quite dense and settle by itself. So you can see on the bottom of the reactor the feeding. You have at the top of the reactor, you have baffle in order to retain the granules inside the reactor, and then you recover the biogas and the outlet at the top of the reactor. You have some picture of some granules. As the granules stay in the reactor, you can apply quite high organic loading rate, up to 25 kilograms of CO2 per cubic meter and per day. The retention time can be decreased down to 0.5 days. The velocity of the granule setting is about 20-50 meters per hour. So you can get some high biomass density in the reactor, and the height is around 6 meters. Again, some picture of industrial processes of these USB reactors. For example, one in brewery in Belgium. You can also fix the biomass on some supports. We can be either mobile or fixed. In this case, it is the expanded granular sludge bed, and you can make the beads in movement thanks to the liquid flow rate. There are some biofilm reactor of biomass or of some plastic supports. And also, this in the big picture, the supports are mobiles, and on the left, it is cloisonné, it's a fixed support. You can see that the bacteria are growing on the wall of this support. Other biofilm reactor where the bacteria grow on some kind of beads or support, so they can be fluidized thanks to the feed flow rate, or up-down if naturally the support will settle down, or downflow if the support will float at the bottom of the reactor. You can use also membrane reactors, which will let only the water go through the membrane. So in this case, the bacteria are retained in the reactor, and the sludge retention time is much higher than the hydraulic retention time. In this case, you will have very low total solid concentration in the outlet of your process, but the drawback is the need of cleaning of the membrane. When you use a membrane, you can put it inside the reactor. It is the internal membrane reactor, and thanks to biogas, you will remove a membrane fouling, or you put it at the outlet of the reactor, so you will need an additional pump, and you will recirculate your retentate into the reactor. There is a summary of the different processes, from the simples, the anaerobic lagoon, to the most sophisticated. And you can see that the lagoon will have the highest hydraulic retention time and the lowest loading rate. And after, as you retain the biomass into the reactor, you can increase your organic loading rate and decrease the hydraulic retention time. This is as a summary of the wet processes. The advantage will be the simplicity of pumping and transfer, and you can also do, if you use some solid material, you can do the hydrolysis in the pulping reactor. It's some kind of two-stage reactor. But if you use some substrate like straw or manure, you can see some floating layer at the top of the reactor, or on contrary, the sedimentation of the most heavy material, and also you will need a large volume of material. In contrast, the dry processes will have the advantage of having a smaller volume and to use more substrate, but as a drawback, they will have some complexity of the solid matrix. They are a simple process, and we don't know very much about the plant operation or performance criteria. So now you can see it's about the dry process. They can be either continuous or batch process. In the case of continuous, generally, if you have solid feedstock, you will need to mix it with water and then introduce in a reactor where you will have a total solids content of 20 or 30%. The digestate will be will go through phase separation, such as filter press, to get the solid digestate, and the liquid digestate can be used to provide some water to the digestate. So this process will be used for large plants, for example, fermentable fraction of municipal solid waste and green waste. And there will be different strategy, different technology according to the mixing strategy. You can also have some batch reactor. Usually they are smaller. Yeah, you would put everything in your digester with more or less the same total solid content, and you will recirculate some leachate into the reactor to bring microorganisms and water as well. The small ones are more used in small agricultural plants, treating manure agricultural waste. So now here are a few examples of continuous process and the Valorga process. And the particularity is the mixing is provided by some will be provided by some biogas recirculation. So it is, well, I think it's only used for municipal solid waste with, you can see the TS contents, organic loading rate of about 5 kilogram VS per cubic meter and per day, retention time between 15 and 30 days, and they can be operated as thermophilic or mesophilic temperature. This is a real picture of this process for municipal solid waste in Amiens. It's a French town, and it was the first process which was constructed for municipal solid waste, and it was in 1988. So the capacity is 100 tons, 100,000 tons per year, with the main feedstock at municipal solid waste, green waste and agro-industrial waste. They have 3 digesters of 2,500 cubic meter and 1 on 3,500 cubic meter. And the biogas was used as steam to heat industry. This is the CompoGas process. It is a horizontal one. And the mixing, it's like a plug flow process. So the feeding enter on the left side, and it will be at the outside after the hydraulic retention time of around 20 days. And here you can see that the mixing is made by different transversally agitators. You can also have at the outlet solid separation to recover some liquids for the process. Here is the real picture of this process. And it is also in Montpellier for the municipal solid waste, treating 170,000 tons of municipal solid waste per year and 33,000 tons of bio waste. You have energy production which correspond to 29,000 megawatt hour of electricity. A more complete picture of this of Montpellier plant. Yeah, you have the reactor here. Another process is a Dranko process. It can go up to 50% TS, organic loading rate between 10 and 20 kilogram VS per cubic meter and per day. Hydraulic retention time between 15 and 30 days. Again, can be operated in thermophilic or mesophilic. And now the mixing is operated thanks to the circulation of the digestate with fresh feedstock. And yeah, the batch reactors that are more operated at farm biogas plant. So you can see the garage where, thanks to the tractor, you put your waste. Most of the time it will be manure, which and also some digestate, and you will throw some liquid through the garage. So they are made of concrete cells, and they are fed. Usually they have 4 or 6 cells because it is continuous process, and they want it's batch process, and they want some continuous production of biogas. So they should start one reactor each 10 days or 2 weeks. This is the example of a reactor in France. It's an agricultural reactor. It's on a farm which is 70 hectares. It has 50 cows and 500 rabbits. So it will treat 1,500 tons of manure per year. And thanks to that, it can produce 30 kilowatt-hours of electrical power and 60 for thermal power. For that, it adds 4 digesters of 100, almost 200 cubic meters. It is a batch reactor, as I just previously showed you. Here are some examples of reactor in China. Maybe you can see the legend. You can read it more than me, but the number is very high in China. They have a number of plants, and it can be either at house scale with they treat the residue from the kitchen residue, the manure from animals, and direct use the biogas for cooking. At the opposite, they can have very big digester plants, which in this case it treat 500 ton chicken manure per day for the production of 3 megawatt hour. So I have more or less finished. I just want to present you some picture. The first one, it's the slug digester from Switzerland. Then you have the egg-shaped digester. This is the anaerobic digestion of municipal solid waste. That process. It is near Paris in France. Yeah, municipal solid waste anaerobic digestion in Barcelona, in Spain, the Valorga process. This is a siestier as a agricultural plant, farm biogas plant, and you can see 4 agitator. Lateral agitator and one central one. It's in Sweden, it's small pilot by a farm biogas plant. Another Dranko biogas plant fed with energy crops in Germany. They are using a lot of energy crops. Another for pig manure in biomass in Germany. And finally, the batch reactor at the farm scale. Well, thank you for your attention, and we'll be happy to answer your questions.
Okay. Thank you. Masuk, Pak. Masuk, Pak. Suara aku masuk. Thank you so much, Dr. Hélène, for your very interesting presentations. So before we go to the discussion sessions, we still have one follow-up questions from Mr. Mulyadi. So maybe you can read in the chat. So it's still, he is not really understand whether or not we could like specify using only one bacteria in the anaerobic digestion. Is it possible if we only use one bacteria? Is it possible or is it challenging?
No, bacteria will not do all the steps. You can use one bacteria to make the hydrolysis, but it will be less efficient as a mixture of them. And after you will have other ones to produce VFA and then methane.
So, Mr. Mulyadi, so we can, as I get from Dr. Hélène, we can use one bacteria for the one every of the stages, every of the process. Yeah, like
I can hear what you are saying. So.
oh.
So we have so when we are researching specific bacteria, we can use only one. He is asking, can we only use Clostridium for the process, like the whole process? We only use Clostridium. Is it possible? If we are doing something like
yes, but the Clostridium will make the first stage. Clostridium cannot produce methane.
Oh,
it will be only the first stage. And
I see. I see. Okay, so every bacteria has their own role, yeah, in the anaerobic process, and it cannot only be done by only one specific bacteria.
Yeah.
Okay, thank you so much. Hopefully it answer your question, Mr. Mulyadi. If not, please feel free to add more. And next, we have one question again. Another question from Miss Yenita Sandrasari. I like reading your articles. One of your readers. My question: in Indonesia, highly populated settlement, how do you think the practical recovery alternatives are for reuse wastewater treatment and biogas utilization? The recovery alternatives. Municipal wastewater
municipal wastewater treatment. Well, the problem is for municipal wastewater treatment is very low concentration in STUDI, and as we have to eat the reactor, we will spend a lot of energy to eat the reactor as the content is quite low in energy. I think it can be possible in Brazil or in hot countries, maybe in Indonesia. I don't know, but in Europe it's not either. You have to concentrate it with like precipitating or things like that before sending to anaerobic digestion.
Okay. So we need a pre-treatment
Yeah.
for that. Pre-treatment, whether it's becoming like a block or drying it first, something like that.
Yeah.
Okay.
And the second problem is the thanks to anaerobic digestion, we will never go down to very low value of COD at your outlet. So you still need some finition with aerobic process.
Okay. So there's still aerobic process. So the combination between the aerobic and the aerobic process is something maybe practical to be implemented here in Indonesia.
Yeah.
And with the hot and even practical weather.
Yes, if it is 30 degree of here, yeah,
Yes.
so it will be easy or maybe it may be very interesting. So if you
Okay.
don't have to eat the wastewater, it will be fine.
Okay. Okay, well, maybe it will be easier here in Indonesia.
Mhm.
Okay, any other questions, participants? You may now, if you would like to directly ask Dr. Hélène, you can raise your hand in this Zoom. So I can see you're willing to ask something. Is there any other questions, participants? So, yeah. We have no other questions, I think. So maybe if not, I have one question. Maybe quite a silly, but yeah, we are learning right now. So among all the digestion process to generate energy from the waste, was from your side, what is the important steps? Like, to be able to gain as much energy as we can from the digestion process. What is the most, the most important steps
Uh,
we should do?
from which waste? From wastewater or solid waste?
Solid waste.
Solid waste. Yes, well, I'm working on pretreatment of the waste to improve this and the energy recovery, but the problem is they cost. It is already the anaerobic digester has a quite as cost, and you should add another cost. But also, most of the time, you can have the same results either as a pretreatment or by increasing the hydraulic retention time. So this is yes, this both point should be considered, I think.
Thank you so much, Dr. Hélène, for your answer. So again, now the opportunity is open for all the participants. If you would like to ask directly to Dr. Hélène, you can raise your hand or just chat. If you are not comfortable talking in English, you can talk in Indonesia and help to translate as much as I can. So please, all participants. So we have 76 students here listening to your lecture.
Thank you for being here. Thank you for your attention.
Thank you so much, guys, for listening to this lecture. And again, it's opportunity for you all. If you would like to learn more about the anaerobic digestion. And as we see from another perspective, I see this kind of process is very beneficial to deal not only with the waste problem, but also to generate energy alternative. As
Yes.
we are not trying to, phasing out from coal and etc. And how do you think will it contribute to the wider climate change issue also?
Yes, but I think one for climate change issue, the first is to limit the generation of waste. The best waste is not produced, and this has the advantage of recovery part of waste as energy, but also as fertilizer, and as we can recycle it. And as you know, fertilizer is very energy intensive for the production, so it is a double production. But also, I think it would be very useful to treat also municipal solid waste. But for that, we need to sort it. So we have to separate the organic fraction from the glasses, the can, metals, plastics. This is quite an important step also.
So yeah, as I noted, Dr. Hélène stated that this process is very beneficial, not only dealing with the energy alternative, but also to provide fertilizer alternative dealing with soil and etc. But one important thing to note is that we really need to sort the waste first, like the solid and then the sludge and maybe all the organic and plastics and glass. We need to separate that at the very first step before we could utilize it and enter into this anaerobic digestion process. So there's a lot of problems that we could solve through this presentation from you. It's really interesting. So again, I'm opening this floor to all participants. Please, if you have any questions or issues or discussions, or you would like to share something, I see you also have some of the officials, I think. So the officials here. If you have any from the government or anything, guys, if you have anything to share, please feel free to use this floor. So maybe would like to ask more. Within you are one of the topmost cited author in the Carrere analytics. So what maybe would you mind to share tips or maybe a strategy? How can we develop an article that is being cited by a lot of other authors? Like, writing article is hard, but how to generate an article that could be cited by other articles
Okay.
is hard. So
In general, the most cited paper are review paper. Because when the students start making bibliography, it's easier to get some synthesis of some knowledge. And after, when they start writing a paper, it's very useful to have such kind of paper. So write a review paper when they are some room. This is the first tip. And as I insisted yesterday, try to make some novel research. You have to find the novelty of your paper to put it forward. And first, it's easier to publish it, and it may interest some people.
wow.
And also another point, to write as clearly as possible. If people need 2 hours to read your paper, they don't understand your sentence and things like that, they don't they do not go through it.
There's 3 tips ways to write an outstanding paper. The first is you have to create a good article. The second one, you create a novel. You have to be published or perish. you have to be the first researcher that publish your research, your novel research, and the last is your writing shall be really as clear as possible, so people could understand what
Yeah.
you're working on.
And another tip maybe not to try to put all your results
I see.
at the same time. You have to select the results which support your conclusion and which make a clear and simple story.
Okay, so as I'm working in my dissertation, so maybe we could every each of the research that setting all the grand research in our dissertation, we could choose one specific research to be published. So it could be more clear.
Yes, it's very difficult for students not to show what they have done, but we know that most of the time they did a lot of work. But you have put it apart to try another paper or put it in supplementary material.
So guys, if you have a lot of work, just stay patient. You could write it one by one, or maybe just one simple question. So not to put too much anything in an article. So be specific is also important. So again, I'm opening this floor to all the participants. If you have any questions or discussions or anything to share, with Dr. Hélène. You would like to, do you mind, is there any possibility to like visit, be a visiting researcher in your institute? Is it possible?
Well, you have been we have to find some funding.
Yeah.
Maybe I have to check, PhD program. Yeah, we have to check that. There can be some orientations. There can be some co-tutelle thèse also, things
Okay.
things like that.
Yeah.
But it's more on we should have the funding on the project or things like that.
So yeah, if anyone really finding some interesting alignment research with Dr. Hélène and interested to work with her, maybe you can find some funding strategies and try to contact her as well to do research and all those anaerobic digestion projects and French by any possibility, any opportunity, like maybe join Cototel PhD program also. So okay, anyone? Do you have any questions? Mr. Mulyadi, do you have any follow-up questions? You may have the floor. Or Mr. Miss Yanita, you might also open your mic and video if you would like to ask. I don't see any question. So,
Bentar lagi.
My research is and probably my about what do you think about in France and maybe in your city or your region? How you use this technology of the in the macro perspective to control the
Yes, it's quite. I don't.
Is it possible to control the leaching qualities?
Well, most of the time you will have to finish the depollution thanks to aerobic process. Well, generally the strategy is to recover as much energy as possible with anaerobic digestion, and then to get rid of the pollution thanks to aerobic process. But it's more expensive. Some oxidation, chemical process oxidation, population, or things like that.
Yeah, my question is, it's not very detailed and very accumulated, but it's very macro perspective of this policy. You would have to learn from your research or how about research from the finance like this and what kind of technology success will the system to control the research.
Yeah, but which kind of waste do you speaking of? The one which is, which kind of waste?
When you use like
Yeah.
our Yes, from the area of the
everything is good. Well, maybe the first thing would be the sorting. In France, we are no more allowed to, or even in Europe, dumping, not dumping, landfilling is forbidden now. If there are other possibility of recovery of waste, the landfilling is forbidden. So maybe first to separate all kind of material. On one side, the glass, the plastics, the metals, and to try to recover as many as possible. No, this one. It's too easy.
Yeah. We can in chamber we try
Okay.
and we also try to understand how much and how technology we can apply to follow the
Yeah.
I think this is a proper meeting the technology I have
Yeah.
influence is very expensive
Yeah.
for my perspective.
And very loaded.
Yeah.
Concentration.
We can try to study in there how to control the region and everyone is good. And
Yeah. Well, the first step is the leakage recirculation. If you will put it again and again in the block, you can recover some more methane, and also it's beneficial for bringing some microorganism in the tank. And after also in my town, I know we add some membrane reactors. I will make membrane reactor to recover it, to treat it.
my understanding it's very hard. The more not so expensive.
Yeah.
Because
Yeah. Yeah. Yes, and this is that no more metals in the waste. So if the metals are recovered and valorized again, so the pollution will be lower in the leakage also.
Yeah.
It's interesting discussion between Mr. Mariam and Dr. Hélène. All the participants, sorry if you maybe having some very difficulties. So recently we just discussed about how to deal with the chip as the effluent of the landfill. However, in France, speaking of the context, Dr. Hélène, in France, landfill is forbidden. So not dealing with any other leachate problem, but however, to deal with the leachate problem in Indonesia, Dr. Hélène suggests in using the microorganism or maybe to very first, as we discussed before, to sort our waste first and to prevent the landfill itself. But if we are dealing with the landfill, we could use either the membrane or the microorganism to recover all the energy that and dealing with all the pollution that comes within the leachate. So Yeah. Again, to all participants, if you have any questions or discussions, you may have the floor. Anyone? I would like to raise. You might raise your hand directly, whether you are speaking in Indonesia or English, feel free. Or you can also drop your question in the chat.
Hello.
Hello, Mr. Mulyadi.
Okay.
Would you like to ask?
No, I don't want to ask the other questions, but I just want to make it clear the answer because I can catch the answer in advance participate. So I wanna my question answer clearly because basically
I'm sorry, Mr.
Yep.
Mulyadi. Would you mind to wait a second?
hello.
Yeah, wait. Pak, suaranya.
Okay. Is it audible?
Yes, you are audible, but in this room, wait, we have technical difficulties. Yes, your voices, I can hear you, but in the room, we are. Okay, can you speak again, Mr. Mulyadi?
It doesn't really clear actually. I don't know how.
Pakai itu aja. Speaker laptopnya Dr. Hélène.
I think you must use your laptop speaker on your device.
Okay.
It's better, I think.
Okay, please.
Then you use the microphone or the other device.
Yeah, you can.
You can speak.
No, it's not clear.
You can speak, please, Mr. Mulyadi.
Okay, good. Here I am. I don't want to ask the other questions. I just want to make it clear the answer or the answer of my questions previously in advance. So basically, other anaerobic bacteria will also participate in the decomposition process along with the Clostridium bacteria, such as I know there is a bacteria named Methanobacterium. The bacteria will decompose the pollutant to be into methane. So how to avoid this methanobacterium bacteria join Clostridium in a breaking down organic matter? So only Clostridium, no more the other bacteria. Is it possible or not? Or and if possible, I wanna the article support this answer. Thank you. Please.
Thank you so much. To make it clear to Dr. Hélène. So, Ms. He need so the first questions.
Maybe I would like to repeat Dr. Helene's explanations before. She already said that to only use Clostridium is impossible. It's hard.
So
Because every bacteria has its own role. The process of the digestion. And another question from Mr. Mulyadi is that how to prevent a methanobacteria in reducing the methane that is being produced? How can start with bacteria. So
So
please.
Yes, thank you for your question. To come back to Clostridium, now I think I understand you don't want to make methane, but you want to make hydrogen and BFA. It's working at fermentation. So in this case, it's okay. So if you want to remove the algae, you don't want any methane, there are several solutions. You can put it your inoculum by heat shock, thermal treatment at 90 degrees, so you will kill the algae, the pathogens, kill them, and also you will favorize the Clostridium, which are correlating. So first method. Another method is to work also in acid conditions. So the methanogens need to be the pH neutral pH. So in acid condition you will not have them. And also to work with low uric retention time, lower than the population, the growing of methanogen. So with less in fermentation, still we are speaking of dark fermentation. Usually it's few for wastewater, or it could be up to 2 or 3 days for solid waste. That
So to note, there is some strategies to deal with, to deal with to prevent the methanobacteria things. The first is work in the 90-degree digester and evaporize the Clostridium, and all working in acid conditions. It could also possible, as well as we could lower the population of the Clostridium. It could also help to prevent the methanobacteria things, as you mentioned. And second one is, do you have any reference for this? Like, a paper or articles that you could refer to? So, yes, I have one colleague, Eric Travi, who's working a lot of fermentation. I work a little with him, but if you email me, I can send you some papers. Mr. Mulyadi, Dr. Hélène is very open if you are willing to email her directly. So he could send you some references, since she mentioned that one of her colleagues is working in this matter.
Okay, thank you so much.
Yeah.
Send me the email, Miss. Thank you.
Okay. Thank you so much again, Mr. Mulyadi, for your proactive participations in this discussion.
Okay, thank you.
If there are any other participants that would like to ask in this occasion directly, please use this opportunity, since we still have, I think, 1 hour. If this session, it will go 1 hour again. Any other discussion? Do you want to learn more about waste to energy and aerobic digestion, or maybe asking technical questions like Mr. Mulyadi did? Anyone? So we see none of you asking again. Maybe later in the session, we would share your presentations to all the participants, and within that presentation, Dr. Hélène has shared her email, so anyone that willing to ask her more in detail about any technical questions or anything that you might willing to ask, she is open to that. So, but again, is there any questions? From So I was very impressed watching your presentations is about how the waste to energy reactor is quite established in France. It has such a huge capacity, like, you know, meanwhile here in Indonesia, I think this kind of technology is still rare. I don't know whether it is money problem, like, you know, it's expensive, or it is more like a political problem. So if you might share, is there any, like, you know, how you as the, I think you start this career since 1993 or so. So you might see the changes within the France on how they're dealing in the waste, and how, like, you know, what are the steps, or what are the transition stages to be established as it is right now?
Well, it used to be to treat wastewater effluents in the 70s or things like that. But it started, we started using this process to produce energy when the government changed the price of buying the energy. First, they give subvention to produce electricity. So there has been several cogenerators. And now for more or less 10 years, there's they really want the production of biogas, of biomethane. So the buying price is very attractive. And now biogas have a very fast development at farm scale. And around, they are not all built, but we will have soon 1,000 plants in France. But the main point is the price the government, the subvention the government gives to buy either electricity or biomethane.
So there's a huge role of government in buying this technology.
The
Feeding tariff of the processed waste energy, like the biomass generated electricity, if I'm not mentioning it wrong. So there's a lot of maybe homework. Okay.
I'm because it is my content for this, can you how much people or how much for how much can you get this?
How many?
Okay.
How many people that is involved?
Yeah, in your technology.
Oh, okay.
Yes. Our lab is based on biological process for waste and also various raw mat. So anaerobic digestion is the oldest process we are studying, but we are also working on dark fermentation for hydrogen production or organic acid productions. Now we are also working on microalgae, on photogranules, and on chemical systems. Microbial electrode system. So we are, and also the lab is organized, it has been funded around anaerobic digestion, but with multidisciplinary approach. There are people working on microbiology, on ecology, on process engineering, microbial process, transfer technology, modeling. We also studying the digestive quality. So, and now working with always over process, we are 80% full-time in Narbonne, but among them, about 38 from Carrere. We have 10, 15 and 20 PhD and postdoc. And also we host some industrial.
Yeah, actually, I can say effectively, I just come with my performance of the I can talk about our perspective about and how we can understand the behavior of people and then we try to solve their way by painting the appropriate technology that is not so expensive. This is my concern now. Yeah, I am surprised because I think that your technology is for with other people, but you really say that it's also for with management. So I'm very interested to understand more detail if you want to say about your technology or your calling about this anaerobic system for this maybe as long as it is about the organic waste or food or something, then it is can be problem handling. Even for example, we can call it and we can assess it positively. We just make a paper. I'm sorry, we just make a paper and then publish it. But we not thinking about how the can and how this improve to the process because it is a game. We can find publication for people, but we didn't think about this one. So it's very interesting.
Well, another driver to promote such technology would be taxed on waste. If people have to pay when they do waste, they will find ways to treat them.
Yeah, our problem is when for example, for today, we try to bring the cycle. The people who they will take money from the cycle. But maybe 60% of them is a direct money for adequate. It is the money. It's the money. Yeah, this is our concern now, and we have big number of things in the class that we try to exploring more detail about the anaerobic, not anaerobic. For me, that composting. This is not a deeply about anaerobic in anaerobic, but we just try to make the composting system, and then we try to record. I just study the to having this way. What can you tell me how you understand to maybe getting people involved and how much you try to lead to it? Maybe 1 ton, 2 ton, and then 100 ton, etc.
It's not really my domain, but well, at first I think it's to make people conscientious about I would say the urgency to decrease the pollution, to reduce our consumption, and things like that. And after maybe one thing, maybe some courses for children. They can make them conscious of that they can go on saying, no, we don't have to throw away the bottles and things like that.
So we are just having discussion about how to start initially starting the whole process of anaerobic digestion and how to deal with waste problem. So the first, Dr. Hélène suggests to make people consensus the importance of dealing with the waste and how to, like, make people pay for what they are polluting. So in environmental science, we know the polluter pays principle. So we could use its principle to deal with the waste. So to reduce the waste first at the very first time. And if I may ask, related to Mr. Mariono's discussion, do you have any experience in developing a small scale digester that could be easily implemented in one village, or maybe, to create a self-sustaining community? Do you have any kind of experience dealing with that?
In Europe, I know the small one exists in China or in India, but there's less security rules or things like that. It will not be possible in France or in Europe. And the problem for the small ones in Europe is the capacity of either cogeneration or biogas cleaning. It's a scale, the very small pilots will be very expensive, so we need quite a high amount of production to make it interesting. But I'm sorry, I've forgotten a name. Yesterday I've spoken with a lecturer making a PhD thesis on about a village. Yeah, and she said it's one hour from here. They built about 40 anaerobic digester. Gétrage, the village. Do you remember the name? Yeah.
Andina.
Andina. You have told me.
Okay, thank you. So it is interesting. When we are talking about a small scale digestion, it's less effective if we are talking in French. It's more effective if we develop it in a huge scale. So
Using the biogas for cooking and drinking is perfect.
okay.
One needs some bloody irrigation, it will be too expensive.
I see. So if we are talking about the small scale aerobic and anaerobic process, it will be efficient if we directly use the biogas for cooking or something else. But if we would like to process this further, like using for electricity and so on, it will be less effective rather than the huge the digester. So it needs, like, integrated system within a city rather than creating a small scale of. Oh, that's interesting.
We would like to know, what do you think about the remaining 1,000 workers? Please,
1,000 households. Is it small or is it quite enough to develop such a system that is effective in cost and effective in technology? What do you think?
So I can make a calculation. In French, we speak more about cause, and I think for the smallest one, I think 100 or 200 cause is okay. For the small box, the simplest I'll show you. But I have to check. But about people and household. Sit down.
For small scale, 100 until 200 household. For small scale.
Just because, well, I don't know, example in France where you directly take the household waste. In the digester, it goes through the waste collection, it goes through the municipality. I was speaking of course, because we are cultures, the digester, they manage themselves.
Sapi, kotoran sapi, kotorannya.
Kita pengen belajar juga, tapi intinya itu awal isi. Nah, pengen tahu aja, kita pengen tahu belajar lah. Kalau katakan 100 akal itu gimana?
No.
Ya, bisa jadi.
So it's not in.
Kalau ya, tapi kalau sapi kan cinta.
It's
Kalau kembali ke kalau sapi, ya kalau sapi sih oke. Kita juga paham. Mungkin kalau misalnya pernah juga kalau ya, terlalu masalah itu, saya juga ada kebetulan.
okay. So he's just like confirming the incomparability of the case between the Indonesian and the French and what you have experienced before. So you count the waste from agriculture, like the species of the cows and so on, while Mr. Mariono is asking about how we implement the scale of household that is being solved by the system, by the biogas and anaerobic system and so on. So it's quite hard to compare and to relate. And I confirm it, so it's quite hard to confirm. So yeah, I think in the schedule we still have we still have a lot of time, 45 minutes to talk.
Maybe we can discuss by email or but I will I am not so but my focus is so maybe I will ask many things.
Okay, maybe is there any like closing statements that you might willing to share to the audience, like the key maybe anything that you might as your closing statement in the sessions?
Well, as a word of conclusion, I would say it's quite important to move from a linear economy, taking some resource to the earth and wasting waste, to a circular one with first reducing the production of waste and then to recover as much as possible and then to recycle. And maybe energy for methane should come at the end when we cannot do anything else from the waste.
Thank you so much. That's such for me mind-blowing closing statement. So as we are speaking more technical at the very first time, but now we are closing with a more general topic where she's speaking more about the importance of circular economy. We clearly rules cycle agriculture, all the elements that we think it's just always and we can use it more, but in today's era, we really need to escalate the concept or implement, not only in research, but until we can implement it in our practical process, in our city system. So there's a lot of research ideas actually within this lecture alone. From the technical, like, using the clostridium bacteria and so on, and how this system into a citywide management risk management system, and how we implement it, the circular and the policy. So I think all of the environmental science college listening in this session what many folks discuss insights and learnings from this lecture. So maybe that's all. We could end this session earlier. And as we have mentioned before, the committee will share Miss Dr. Helene's presentations, and you might ask again questions or any other inquiries that you might be interested to share directly or through the committee. And maybe that's all. I am thank you again, Dr. Hélène, for your time, for your energy, and for your effort coming here to here in Indonesia. And I really hope you will have a great stay here experience. And you will have a great in Indonesia, like yeah. So anyone would like to meet her? Maybe we could contact the science group administrator. So that's all from me. Thank you so much again for all the audience and participants of these sessions. I apologize if I made some mistakes or the questions really well, but really fine. Energy. So bear with me. Three o'clock out. Almost almost. Maybe that's all from me. I would offer back this floor to the research center. So, see you. Thank you.
Okay, thank you. Thank you, Dr. Hélène, for your presentation. It's very interesting. And we learn more about anaerobic digest. And thank you for the moderator, Miss Rizkiana, and for leading the discussion. And the next agenda is certificate submission for Dr. Hélène and also closing statement from Head of Doctoral Program of Environmental Science, Dr. Budi Warsito, SSI, MSI. For Dr. Budi Warsito, time is yours.
Okay, thank you very much, Mbak Vilma. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everybody. The Honorable Dr. Helena, Pak Mariono, Dr. Mariono, Head of Study Program of Environment, Master Program of Environmental Science, and also the moderator, Mbak Rizkiana, and all students. Maybe the certificates that Hilma can give them to Dr. Helena. This is the certificate for you. Thank you very much, Dr. Helena, for your contribution. I'm sorry, still a virtual certificate. Certificate hasn't been printed yet. Okay. Thank you very much for your contribution to our study program. And okay, Dr. Helena Carrere, once again, thank you very much. Thank you. Also, thank you for Prof. Purwanto, the supervisor of this physics lecturer, and then Pak Mariono and Pak Fuad, and also the moderator, Mbak Rizkiana and Mbak Vilma as Master of Ceremony, and then also all of students and all of participants, and also all of the committee from Magister and Doctoral Program on Environmental Science. I think Dr. Hélène Carrere has presents a very interesting and very important for the research and publication for resolving environmental problems in this general lecture in this afternoon. And so it is useful for our students, especially in regarding with the publication in reputable journals as a graduation requirement in doctoral and also in master program. We hope that this collaboration, this visiting lecturer and all this general lecture in this afternoon can increase collaboration between doctoral and master program of environmental science in School of Postgraduate Studies with the INRAE of France National Research Institute for Agriculture, Food and Environment. At the end, by saying Alhamdulillahirabbil alamin, officially I close this visiting lecturer and this afternoon. Once again, thank you very much for all of you, especially for Dr. Helena and all of participants. Thank you very much for your participation. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Dr. Budi Warsito. Ladies and gentlemen, we are reached the end of the agenda. Let us close the visiting lecturer with reading Hamdalah together.
Alhamdulillah.
We would like to thank you, the audience, for the participants. We are also apologize if there are words or action that less pleasing. That's all. Thank you for your attention. Assalamualaikum warahmatullahi wabarakatuh.
Assalamualaikum
Waalaikumsalam warahmatullahi.